phone. Ring, 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 ring. Banana phone. I've got this feeling so appealing for us to get together and sing, sing. Ring, 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 ring. Banana phone. Ding dong, ding dong.
I should have written slower. Okay, hello. All right, let's do this. Oh my God. So this talk is titled Methods of Memory Management in MRI, or Ruby. My name is Aaron Patterson, and I have come from the United States to bring you freedom. If you don't recognize me in person, this is what I look like on the internet, so I look a little bit different, but that really is me. I work for a small startup called GitHub. It is the first legit company that I've ever worked for. This also makes me a GitHub certified engineer, which is pretty cool. I'm GitHub certified, and that's because I like to get close to the bare metal. So when I started working for GitHub, I mean, everybody at work refers to each other by their nicknames. So I went to the office, and I usually work from home, so nobody says my name that frequently, just my wife, and she doesn't really call me Tenderlove. So I go to the office, and then everybody there is referring to me by this name, and I'm like, this is really, really awkward. Please just call me Aaron. But yeah, so it's fine to call me Aaron, but if you want to call me Tenderlove too, that's fine. That's fine. I don't mind. I love cats, and the reason I love cats is because cats are the best. I'm going to show you some pictures of my cats. This is my cat, SeaTac Airport, Facebook, YouTube. But we call her Choo Choo for short. This is the more famous cat, Gorbachev Puff Puff Thunderhorse, and I like him a lot. He thinks he's hiding here, which I think is pretty hilarious. This is Choo Choo again. I like her a lot as well. The reason I like her is because she makes a face. This face, this is the same face I do when I'm programming. I don't understand. I'm like, just. Just nothing there. I'm just totally blank. Anyway, I have stickers of my cats, so if you'd like a sticker of my cat, I will give you one. I was actually recently in the news, and I was in the news recently for approving a pull request. So that's pretty cool. I'm actually really, it's really awesome that so many of the speakers here are keyboard enthusiasts. I too am a keyboard enthusiast. This is my travel keyboard. You can't see it too well there, but I have it right here. Here's the physical copy. It's actually got UV backlighting, so you can see those are the UV LEDs. That's so that I can get a hand tan. I don't go outside very often. So yesterday, Martin Fowler was saying, nobody times how long it takes to type the letter E, but here we've got so many keyboard enthusiasts and Vim users, so I know he's wrong. I've timed myself. It takes about 80 milliseconds to type the letter E, so I know exactly how efficient I am with these keyboards. So I want to cover a little bit, a couple new Ruby features. We've been talking on the core team about adding a type system to Ruby, so I want to explain a little bit about what type systems are. So I'm going to show you some types, or explain some type systems. First, we have soft typing, and soft typing goes a little bit like this. Then we have dynamic typing. Dynamic typing is more like this. And then the other one that we're considering is static typing. And static typing looks a bit more like this. You don't move your hand. Static typing. A bit more challenging to implement. Yes! So today I'm going to talk to you about the garbage collector, the GC, and unfortunately this is going to be one long, boring talk. We're not splitting this up. And actually, I noticed there's been a lot of like JavaScript and Elixir and all these alternative languages. I'm going to talk to you about an alternative language today, and that alternative language is C. But first, I want to say thank you. I want to say thank you to all the organizers. They've been really great. Please give them a round of applause. I really appreciate it. I want to say thank you to all the other presenters. Everybody's been great. I'm really, really honored to be the last person presenting today. It means a lot to me. I also want to say, really thank you to especially to the Rails Girls Summer of Code presenters yesterday. They were really awesome. It was inspiring to watch them speak, although one thing is that I think they need to get a little bit better at marketing, because apparently the two that came from Egypt, they had to borrow money to pay their way to get here. So what you should do is you should go to this link and help them cover their expenses. So go there. You can do it. You can do that today. I don't want to go full NPR on all of you, but you really should go to that link. Sorry, that was. I know the other Americans in the audience got that joke. It was really hilarious. Trust me. Trust me. That was a good joke. Anyway, so Martin Fowler, it was really great to watch him speak. I don't know if you know this, but he retweeted me once, which was amazing. Look at that. I saw that. I screenshotted it and sent it to my wife, and she was like, "Oh my god." So I like the presentation he gave yesterday. Like this graph that he presented here with the we've got no design and the good design here and the functionality, and I thought it was very interesting. Except that one thing you didn't really point out about the graph is what the shape of these curves are. This one is clearly ON, and the other one is O log n. So not designing your code is O log n, and good design is O n, and clearly O log n is better than O n, so no design actually scales better than good design, which I thought is opposite of what he was trying to explain to us in this graph. Sorry. Also, I really enjoyed Kei Wu's talk, but I have to, so I want to present all of you with a hypothetical situation. Let's say that you are an owner of a house. You might be a cat, that's fine. Your friend comes to you, and your friend says, "Hey, can my friend tell you a hilarious pun?" And then your friend doesn't wait for an answer, just the other person says their hilarious pun. Now you may be thinking to yourself, you're probably into one of two camps. You're either saying, "Yes, please tell me the hilarious pun," or "No, I don't like to laugh." So all of you that want to hear the pun, please raise your hands. Tell me. Okay, great. And everyone that doesn't want to hear. Okay, we got a couple. Thank you. So yes, all of you that did want to hear the pun, you are in the I'm a cool person and I like fun stuff culture, and then the other group here is the I don't like to laugh culture. I also enjoyed her presentation when she was talking about the Seattle No. I'm actually from Seattle, which is really great. Carrie's also from Seattle. Wait a minute. Do we have anybody else from Seattle in the audience? Woo! Yeah! So, as somebody who is an expert with the Seattle No, let me tell you something about this phrase. Whenever you hear this phrase, it's okay to say no. If somebody ever says that to you, you need to remember, it is a trap. That is a trap. It's not okay to say no. They mean the opposite of that. And unfortunately, her graph was a little bit wrong here. She said that Seattle was some here, I don't know, towards the guest side, and we have British was very towards the guest side. But that's not actually true. Seattle's way over there. And the reason I know this is because I went to the UK once, and I just thought, wow, British people are so forward. Why do they keep telling me what to do? So then Yehuda told me about cargo, and I was learning about how to cargo cult my left pad. And I was trying to write more slides about him, but then he mentioned me, so I just added this slide. Where's the transition? Oh. Okay. Let's get to the long, boring technical part of my presentation. I want to go over some memory terms, just some terms about memory usage in machines. Typically, we divide memory that we're allocating into a stack and a heap, and we're not really going to talk about stack allocated memory. Stack allocated memory is temporary memory allocated for each function in your stack. We don't really do that in Ruby. The virtual machine does this, of course, but it's not really exposed to you as a Ruby programmer. All the objects that you're creating in your Ruby program are heap allocated, so we're going to focus on the heap today. Heap is just unmanaged memory. It's a place where you can allocate some data and it just sits there. It sits there in memory and you can do stuff with it. And you're able to do stuff with that memory no matter where you are in the stack. You can point at it from anywhere in the stack. Now, there's two types of heaps that I want to talk about. We have the heap, which is just the memory in your machine. You have some amount of memory in your machine, and inside of that, we have another heap, which I'm going to refer to as the Ruby heap. The Ruby heap is inside of the machine's heap, but it can point at it maintains all the Ruby objects, but those objects can point at stuff inside of the machine's main heap. So we're mainly going to focus on the Ruby heap today because the Ruby heap is what's actually managed by Ruby's garbage collector, and we're going to be studying the garbage collector today. So this Ruby heap is the thing that we're going to be focusing on today. So we're going to talk about the GC and MRI, and I know this is a Ruby conference and we have a lot of Rails people here, I hope, being on the Rails core team. And I know many of you are thinking, this is we've seen a lot of Rails stuff. This is a Rails conference, and I hope that well, at least I hope it's a Rails conference because I love Rails. So how many of you are running Rails in production? Sorry, you don't need to raise your hand. I just assumed it was all of you. The thing is, wait, okay. I was going to say something trolly, but I decided not to. Never mind. Okay. How many of you are running Phoenix in production? Okay. Oh, not bad. We've got a handful. That's good. Okay. No, I like Phoenix. It's good stuff. So anyway, I'm hoping that you're running into scaling issues. I mean, I hope you're not running into scaling issues. I hope you're not running into scaling issues, but presumably one day you will run into scaling issues. And this is why it's important for you to know about the garbage collector, because you're going to have to tune the garbage collector someday. So what I want you to learn from this talk, or what I want you to take away from this talk, is if you don't know much about garbage collection in general, I want you to learn some of the terminology. I just want you to focus on the terminology that I'm going to present in the presentation. If you do know about GC terminology already, then I want you to focus on the algorithms that we're going to talk about. And finally, after we talk about garbage collection algorithms, I'm going to talk about some new stuff that I've been working on in the garbage collector. And if you already know about this new stuff, then please come up and give my presentation because I am very nervous. So let's talk about GC algorithms in MRI. We're specifically going to look at the GC algorithms used in MRI. There are many different garbage collection algorithms, but we're going to look at the ones that are used in MRI. There's really two sides of a GC. There's the collection side and the allocation side. So typically we're going to cover the collection algorithm. This is how Ruby gets your memory back, or how it reclaims memory. And then we're going to talk about the allocation side. Then we're going to start looking at some introspection APIs in the GC so you can study how your GC is, or how your garbage collector is behaving. And then we're going to look at some tuning variables. So we're going to start off with the collection algorithm, but first we have to look at some cats. This is my cat. He has some hands. What type of collector is the MRI collector? Well, the MRI collector is a mark and sweep garbage collector. It's generational and it's incremental. We're going to talk about what each of these things means. So at a high level, what does the garbage collector do? At a high level, like imagine that we have some objects in our system. We have a data structure that looks like this. A equals some array of stuff, and that array is a hash. And the way that this is represented is it's represented as a tree. So we can imagine that we have this root node. You can't see the root node. It's not any of these variables. It's just some conceptual object. That root node points at the A variable, which is our array. The array points at the hash. The hash points at the key and the value. So you can see how we get this tree data structure. So let's say we assigned A to nil, and we cut that link between the root and the A variable. So in that case, the garbage collector has to find all of these nodes that are no longer attached to the root and then free them. So that's what the garbage collector's job is to do, is to find those unlinked nodes and free them. So important words from this are, we have a root set. The root set are those root nodes, that one at the top, we can have one or more. Then there's garbage. Garbage are objects that are no longer referenced from the root. Those are objects that we can free. And then we have live data, and live data, those are objects that are referenced from the root node. So the GC's job is to find all unlinked nodes and free them. But how do we find those unlinked nodes? The easiest way to do it is with mark and sweep, and the mark and sweep algorithm, and unsurprisingly, it has two distinct phases. The mark phase and the sweep phase. The mark phase goes something like this. Let's say we have a root node and it points at some data like this. What happens is we start at the root node and we follow those arrows. We follow those edges. And following those edges is a process called tracing. So we follow the edge, we mark A, we mark F, then we follow all of those edges. We mark A, D, B, C, and we keep repeating this process of following those edges and marking those nodes. And once we're done with that mark phase, once we don't have any more edges to follow, we say, okay, we're going to move on to the sweep phase. We look at all the nodes that haven't been marked, and we know that those are not referenced from the root, so it's safe to free them. So we sweep those away. Then when we're done with that, we say, okay, we're going to unmark all the nodes. Once we unmark all the nodes, we allow your Ruby program to continue, and then at some point in the future, we repeat that process. So this algorithm is very easy to understand. The only problem with this algorithm is it's too slow. If we could reduce the number of arrows that we have to follow, it would save us some time. And the other main issue with this algorithm is that we have to stop the world. We have to say, okay, we let your program run, then we stop, and then we do some garbage collection, and then we let the program run again. So we have to stop the world. So you get these halts. And you may have noticed this if you're running a big program and printing out a bunch of stuff. Once in a while, it'll just stop and then continue again. So this is called stopping the world. It stops the world and walks all these objects. And unfortunately, it has to visit every object every single time. So if we could reduce, it visits every single object every time, and it walks every single object every time. So if we could reduce the number of visits and walks that we have to do, then maybe we could speed this up. And the way we do this is through generational algorithms. The generational algorithm hypothesis is that objects die young. Okay, so we know that most objects are going to die young. So if we could take objects if we could divide objects into old and new and only look at the new objects, maybe we could reduce the number of objects that we have to look at on each garbage collection cycle. So the way this works is, say we have two generations here, generation 0 and generation 1. 0 is our new generation. Now, when it comes time to do a GC, we do our normal mark and sweep phase. So we go through and mark A and D, and then of course we mark B and D, and then A and C are unmarked, so we sweep those away. And once we're done with that, we say, okay, well, we're going to promote these into an older generation. So they move over into this older generation. Now we let your program run again. And let's say your program allocates some new objects. Those get allocated into the new generation. And we repeat the process of doing mark and sweep, but we don't look at those old objects anymore. We say, well, we know that those are old. We're not going to follow through with those old objects. We're going to start from the root, but we're only going to trace to new objects. So we do this mark and sweep again. F, G, D get marked, and then we sweep away E, and then we move F and G over into the older generation. So we end up with something that looks like this, and then we unmark again. So the advantage of this algorithm is you'll notice that we didn't have to touch B. So we never visited B, we never looked at B, and we never looked at the arrows that came out of B. We didn't have to touch B at all. So we're able to speed up this process. But there's one slight problem with this algorithm, and that's that, let's say we have an example like this, we let the program run, and somehow something happens and the D object allocates a new object. It allocates something new, and that new object goes into the new generation. Now we know that we're not going to examine older objects. We don't walk that arrow. So when we go to the mark and sweep phase, E never gets marked. So E gets swept away, but it's actually live data. D was pointing at E. So this is an error. We'll get a seg fault or something like that. And we don't want this to happen, so what do? The way that we deal with this is we use a thing called write barriers. So what a write barrier does, all a write barrier is a piece of code that gets executed when an object is written to. So when that arrow is written to D, we have a piece of code that remembers that D was written to. And we put D into what is called a remembered set. And we keep track of that. Now, we put that into a remembered set. So when we do that right there, we remember that. Now we know that D is a new root, and we can visit all the outgoing edges from that root. And then E gets marked correctly and moves into the older generation. And then we unmark it, and again we have everything is good. We've moved all of our objects into the older generation. So important words from here to remember: write barriers, it's just a piece of code that executes when the object is written to, and a remembered set. Those are the two main things we have to remember here. Remembered set, put it in your remembers. Okay, sorry. So the generational algorithm is faster because we don't have to visit all of these nodes, but it's not so easy to implement. And unfortunately, it's also a stop the world allocator. We still have to stop the world and do all of that visiting. So a way that we can speed that up is we can introduce something called incremental garbage collection. And what incremental garbage collection does is it says, okay, well, we're going to do some of the GC, we're going to stop the world, we're going to do some of the GC process, but a very small amount of it, and then continue again, and then stop again and do a small amount of GC. And we keep repeating this over and over. And the idea is that maybe we stop more frequently, but those halts are very small, so we're actually able to improve the throughput of your program. And the way that we do incremental GC is through a process called tricolor marking, where we have 3 different colors. We group objects into 3 different colors: white, black, and gray. White objects will be collected. Black objects have no references to white objects, but are reachable from the root. So these are live data objects. Gray objects are reachable from the root, but we haven't actually looked at them to see where they point to. So the algorithm is, we pick an object from the gray set, we have a gray set of objects, and we move it to the black set. Then for each object that black object references, we move those objects into the gray set. Then we repeat steps 1 and 2 until the gray set is empty. Then we know we've traversed through the entire tree. And this is kind of hard to understand in writing, but if we look at a tree like this, if we look at a picture, we can actually understand it a bit better. So we start out with the root node as black, and it points at A and F. Those are in the gray set. So we take A and F out of the gray set, we mark them black, we visit all of their edges, put those into the gray set, they become gray. We pick objects out of the gray set, mark them black, visit all of their edges, and now we're left with only white objects, and we can sweep away the white objects. So they get swept away. Now, why is this important? I have to do this transition. This is I worked very hard on this transition. You can imagine those gray nodes as a wave sweeping through your object graph. So you have this gray set of nodes sweeping through the graph. So what is the benefit of this algorithm? The benefit of this algorithm is that we can stop it. We can interrupt it at any time. We can do step 1 and then stop and let the program continue again. Do step 2, stop. So we can do these steps incrementally. Each step can be performed incrementally, hence the name incremental garbage collector. This reduces our halting time, but unfortunately we have another problem with this algorithm, and that's, let's say we have a tree that looks like this, hand wave happens, your program runs, and somehow the GC runs, and A and F get marked as black. Then your program runs again, and F somehow allocates a new object. So it does it through some way. We don't know how, but it does, hand wave. It allocates a new object, so it points at G. But if we remember our algorithm was, we don't visit anything that black nodes point to. So we have this problem again where we say, well, we only visit gray nodes, so we mark all the gray nodes black, and now we're done. We're out of gray nodes to visit. So we'll do a GC, we'll sweep everything that's white, we sweep away that white node, and now we have a problem. We have this arrow pointing into nowhere, and we'll get a seg fault. So how can we fix this? Again, we use the same technique we used in the previous example, and that's we install a write barrier onto F. So we keep track of any time somebody writes to that F object, and we know that, okay, somebody wrote to F, we now have to visit all of the things that F references. So important words from this are incremental. We're incrementally doing the garbage collector. We have a write barrier again, and we're just using that write barrier. Remember, it's just a piece of code that gets executed when an object is written to, and we put those objects into a remembered set. So this incremental algorithm minimizes tracing, so we don't walk very many arrows. It decreases halting because we're able to do a little bit at a time. So it speeds up the throughput of our garbage collector. Now the things our garbage collector is not parallel. It cannot run in parallel. We can't do GC at the same time as running your program. It is also not real time, meaning that when we do those halts, we can't guarantee how long it'll halt for. So we can't give you a guarantee that if you run this particular bit of code, that particular bit of code is going to take 50 milliseconds every single time. We can't make that guarantee. That's very important for things that are running on like embedded systems, for example. And there are GC algorithms that are tuned specifically for that, but MRI does not have that. If you want something like that, take a look at MRuby. Or not this presentation, MRuby, but MRuby. So an interesting thing is we're also not a compacting garbage collector, meaning that when you allocate an object into the heap, or into Ruby's heap, it stays in that particular position. It's never moved. It stays where it is in memory. So we're going to look at the allocation algorithms that we use now. But before we have to look at some cats. Those are my cats. That is me with the cats and the selfie stick. So we're going to take a look at the heap layout. This is Ruby's heap, not the main CPU's heap. This is Ruby's heap. Ruby actually allocates large pages, and the reason it does this is because malloc isn't free. Like 3 C programmers in here get it. So rather than doing a malloc for every single object, we'll actually allocate a large chunk of memory and then divide that chunk of memory up into your Ruby objects. So we allocate a large chunk, which is called a page, or I prefer to call it a slab, and you'll see why later. But this page is a contiguous piece of memory. It's just a contiguous slot of memory. So each of these pages holds a linked list. Now, each of the nodes in the linked list are called slots. And each slot is a Ruby object. So if we take a look at this, visually, we'll allocate a large page, and inside that page is a linked list, and that linked list just contains Ruby objects. So all of those Ruby objects are contained inside this page. Now, that linked list, when it's empty, it is referred to as a free list. So all we do is we say, well, when it's time to allocate a new Ruby object, we simply take where the list is pointing right now, we move the pointer forward to the next element in the list, and that gives us the next free slot. So we move to the next space in the free list. This is called bump pointer allocation, where we're just bumping a pointer forward. So let's say we end up with full pages. We allocate all the objects in a page. So all the objects get allocated. What the garbage collector does is it says, okay, I'm just going to create a new page. We'll create multiple new pages, and we'll allocate those new pages, and then you can allocate new objects in those pages. Now, Eden pages, this is a term to remember, is that Eden pages are the pages that we search for when we're looking for a free area. So you can think of the Eden pages as where objects are born. So when GC happens, we'll actually remove the object from the slot, and then we can allocate in that slot again. If all of the objects get removed from that slot, then the garbage collector will say, hey, this page is empty, and we can actually deallocate this page. So it'll free up that page. So important words from this are that we have slots. Slots are Ruby objects. Slots are inside of pages. Pages are just a slab of these objects. And Eden is where we search for we search for a place to allocate an object. And a tomb, the tomb is where the pages go to die. These terms are, I mean, I guess it works, but whatever. So I want to talk about some interesting allocation hacks. I love this. This is a very interesting allocation hack. You may or may not know this, but not every object in Ruby requires allocation. So we know that everything in Ruby is an object, but not every single object is allocated. So we're going to learn how to see this, and it takes a little bit. But one page, we will get there, but just trust me, we have to start out here. One Ruby page is 16 kilobytes. Okay, now one object is 40 bytes. Oh, sorry, I should have mentioned, the objects in Ruby that don't get allocated, the ones that don't require allocations are like integers, true, false, nil. I think there might be others, but those are the ones I can think of now. We don't actually allocate any objects for those. So anyway, one object is 40 bytes. When we do a page allocation, the pages are aligned. So we don't use a malloc, but we use an aligned malloc. And what that does is it says, okay, operating system, give me a chunk of memory, but I want the address of that chunk of memory. I want the address to be evenly divisible by some particular number. Okay, we give it that number. We say we want you to be evenly divisible by some number, and we'll choose our multiple. Our multiple is going to be 40. And you'll notice that is key. We choose 40 because our Ruby object size is 40. Now, remember that we have a contiguous slab of memory, and it starts at a multiple of 40. So if we print this out, we say let's start at 40, and we'll increment it and see what that number is in binary. So this is hard to read here, but imagine that we're moving forward through the slab 40 bytes at a time. If we look at the binary representation of those numbers, you'll see that it looks like this. And you may notice that there's a pattern here where those numbers in binary always end with 3 zeros. Okay? They always end with 3 zeros. So anytime we're looking at a pointer in Ruby in memory, we can say, well, if this pointer ends with 3 zeros, we know it's a Ruby object. Okay, we can say, well, we know, it ends in 3 zeros, we know it's a Ruby object. And what's cool about this is we can actually add meaning to those bits. Like, let's say we change one of those bits to a 1. We would know that that's not a Ruby object, it's something else. Okay? So we can actually use those bits to add meaning. We can represent integers without allocation. So the way that we would do that is, let's say we encode the integers into binary, and the way that we encode them is, let's say, for example, we're going to encode the number 2. We have a flag which is 1. That's going to be our last bit. We take 2 and we convert it to binary, and you see that 2 is 1, 0 in binary. And then we shift that left 1, and then we add our integer flag. So we represent the number 2 as 101, and you'll note that last bit is no longer a 0, so we know this is not a Ruby object. We say that last bit means that this is actually an integer. And what we can do is say, well, okay, we know that last bit is a 1, it's an integer, so we'll decode it, we'll shift it over 1, and there we go, we have our integer back. And we can actually see this today in Ruby 2.3. So we can calculate what the biggest fixnum value will be. So if we look at 2 to the 64 minus 1, you'll see that that's a bunch of 1s. But if we look at the class, that's a big num. But if we subtract 1, let's say 2 to the 63, it's still a big num. 2 to the 62 minus 1 is now a fixed num. And if we say 2 to the 62, that's a big num. So this is actually before Ruby 2.4. If you try this code out with Ruby 2.4, unfortunately you'll see this. They're all integers. And it's because we've consolidated those classes together, so everything is an integer. But what this means is that fixed nums are singleton. We can calculate the maximum fixed num size because, oh, excuse me, I forgot to explain this part. Why is it, my machine is 64 bits, so why is the biggest fixed num 2 to the 62 minus 1? Well, we have to subtract 1 bit for the sign. Now, we know from our encoding that we shift over 1 bit, so we have to subtract that bit as well. So we go from 64 minus 2 is 62. So that's how we can calculate our largest integer. So fixed nums are singleton, and you can see that if we do 2 to the 62 minus 1 and we check the object ID. This is, don't tell anyone I told you this. Is this being recorded? It's probably being recorded. Don't tell anyone I told you this, but the object ID is based off the location in memory where your object lives. It just looks at that pointer, and that's how it determines what the object ID is. So if we take 2 to the 62 minus 1 and check the object ID, you'll see it's a giant number, which I think is kind of cool. And if we turn it into a big num, we do 2 to the 62 and we check the object ID, you'll see that's actually a small number. And if we do it again, you'll see it's a smaller number, but a different number the second time we do it. And this is because we're actually allocating those big nums. Those big nums get allocated onto the heap, where those fixed nums did not need to be allocated. This technique is called tagged pointers. So we're taking these pointer values and taking those last 3 bits and applying meaning to them. So tagged pointers, the different tagged pointers we use, we have fixed nums are tagged, floats are tagged, true, false, nil, and symbols. So many of those we don't have to do allocations for. So I want to talk about some allocation problems. That was just a super cool hack that I love. Manipulating the binary like that, I don't think you're going to do that in Elixir. We're doing a lot of mutations here. All right, so unfortunately, we have some issues with poor reclamation. So let's say we fill up some pages and we do a GC, and some of those objects get removed. We freed them up. Great, that's great. What would be cool is if we could take those objects and rearrange them such that it looked like this. We take those, we rearrange them like that, and now we have a page that's completely free, it's empty, and we can deallocate that page. Great. Nope, we can't do that. Oh, I should have said wrong. We can't do that. Objects in Ruby do not move. So since they have to stay in the same location, it means that we've got this wasted space. We've got these holes in the pages. That one page, we have a page worth of memory that's actually free, but we can't get rid of it. We can't reclaim it because those objects won't move. This causes many issues, among which is copy on write issues. And I want to explain the copy on write issues. As I was talking about earlier, we have Ruby memory pages. We call them pages, but unfortunately the operating system also has pages, which I think is very confusing. So this is why I prefer to call Ruby pages slabs. Now, a Ruby page is not, the size of one Ruby page is not the size of one OS page. The size of one Ruby page is about 16 kilobytes. One OS page is about 4 kilobytes. So one Ruby page is 4 OS pages. Now, let's say we have one page and a parent process and a child process that both point at that page. Now, let's say the child process allocates a new object. That new object is going to be written into the page. And unfortunately, that means that that page cannot be shared with the parent process anymore. We've done the writing, now we have to do the copying. So the OS actually copies one page at a time. So even though we wrote 40 bytes, we actually got 4 kilobytes copied, unfortunately. So I've been thinking about a solution for this, and the solution I've come up with, it's fairly simple. The solution is, so far, is to group old objects. We can do this technique without actually moving objects around in memory. So let's say we have 2 pages. We have a page that is a probably old page, and we have another page which is a unknown page. Now, if we have an object that we know is probably going to get old, we'll stick it into the probably old page. If we have an object that we don't know about, we'll just stick it into the normal pages. Oops. So what is going to be probably old? We can determine that with some heuristics. For example, we know the class foo is not going to get garbage collected. Probably that object new isn't going to get garbage collected. The frozen string won't be garbage collected. So we can apply some heuristics to that. Another idea is that maybe we could determine this statistically. So let's say that 80% of the time we allocate a foo object, the foo object becomes old. So maybe next time we allocate a foo object, let's allocate it into the old page. This helps us efficiently use space. It also helps us reduce GC time, and it's copy on write friendly. So I want to show this. I've actually implemented this. This is some of the GC work that I've been doing for GitHub. But first is a cat. And I'm kind of embarrassed to show this. That is her tongue. She's got a ridiculously long tongue. I think this is why my wife doesn't like her, but I think it's adorable. You can see the tongue there. I'm pretty sure she can like clean her eyes with that tongue. Like look at. All right. So let's say we have, here's our key. Let's say we have red squares, or maybe they look black on the screen. Dark squares are objects, green ones are classes or modules, and white ones are empty. So if we visualize our heap, if we take our heap and actually turn it into an image and look at that, it'll look something like this. This is what it looks like. This is a vanilla Ruby process. And you'll see like there's a bunch of red squares, and you might be able to see in there's some green squares, and a lot of white ones in there. Each vertical line is a page, and each of those squares is a slot. Now, if we take my patch, apply my patch where we have an old page and new pages, and we look at that, you'll see we have a solid green line there, which is where we're allocating all of the class and module objects. They're allocated together. Now, if we compare those two together, you'll see that my version is actually wider, meaning that there are more pages allocated. So the default running Ruby with an empty program actually results in using more memory. Now, if we apply this to, say, a Rails application, so this is a simple Rails application getting booted. You'll see this is without my patch. You'll see a bunch of green objects in there and a bunch of white space. If we compare this to a heap that's using my patch, you'll see that it looks like this, where we have a bunch of classes and modules allocated together. And if we compare those together, you'll see that my patch version is actually slimmer than the original version. We end up with actually a 17% smaller heap. So I want to show you, which I think is pretty amazing. I want to show you another technique that I've been working on for reducing the heap size. This is a video of it. I don't remember if I have to click next to start the video. Oh, I do. Okay, there we go. So basically what you do is you take the mouse and you click over there, and then you drag it to the left, and there you go. Now you have an even much smaller heap size. All right, so let's move on to some GC introspection. So we can get access to GC information by just doing gc.stat, and there's a lot of keys in here, and I'm not actually going to explain any of the keys to you, and the reason I'm not going to do that is because going through this entire process of looking at how the GC works, looking at the allocation algorithms and the collection algorithms, getting those keywords, now that we understand how those algorithms work, all we need to do is look at the names of these keys and it'll make sense. You just read the key name and you know, it's part of, that controls how many slots we have open, or that's how many slots we have available, that's how many we've used, that's how many pages we have available, how many are in the tomb, how many are in the Eden. We'll understand all of the keys. We can also get GC performance information by using the GC profiler. This is just an example of it. You do GC profiler.enable, and then run your program and then ask for a report, and it'll tell you how long we've spent in the garbage collector along with other information about the GC. We can also introspect on the heap by using dump all. This is the API that I use to generate those graphs. And actually those heap layout graphs were HTML pages where each of those squares was I know all of you people are going to kill me for this. each of those squares was a TD tag. With a class, I just put a class on it, allocated, not allocated. And then added CSS for this. I was like, you know what, it works, whatever. I should probably refactor, but I don't care. Anyway, so this is what I use. This dumps the entire heap, but unfortunately I had to add a patch to this which dumps empty slots as well. If you use this today, it'll only dump slots that are actually allocated, so you can't get an idea of what the heap actually looks like. You'll get all the objects in memory, but not any information about what slots are free or where those slots are. So this is what that API looks like. You'll get a JSON dump of that. This dumps just one object, so you can get information about one particular object. And we were talking about write barriers before. You can see right there that WB protected. You know what a write barrier is now. This object has a write barrier, so you can tell from that key. And it's kind of cool. You can see the memory size of that and the type. And it doesn't show it now, but let's say we take this object and we run GC a few times. So we'll allocate a new object. We dump it, run GC, dump it, run GC. We do that a few times, and you'll see eventually we get this key that says old true. So you can see that it actually requires 3 garbage collections. An object has to survive 3 GCs before the garbage collector will consider it to be an old object. So objects have 3 generations. Just check out all the APIs on object space. It's very helpful for inspecting your Ruby processes. Trace object allocations is very handy as well. You can use this to track down where those objects are being allocated. I want to go over, I'm going to close here with a few GC tuning features that are completely undocumented but are what we use in production. This is an environment variable called RubyGC heap free slots. So if you set this environment variable, you can control the number of free slots that are available after a GC. So after a GC runs, you'll have this number of slots available. So another one that we have set is RubyGC heap init slots. This is the number of slots that you have available when you start up the Ruby process. So the other one that we use is RubyGC heap growth max slots. And what this does is it says, okay, when we grow the heap size, we're growing by a certain percentage every time, but we don't want that to get out of control, so we'll cap it at this particular amount. And the way that you want to tune all of these is you want to take a look at how much memory your requests are taking and tune the garbage collector such that you have enough free slots for any particular request to fill out that entire thing. What you want to do is you want to avoid allocating pages during a request. So with that is the end of my presentation. Thank you so much for having me here. I am very honored to be here.